The tutorial today is regarding designing a 4-bit Johnson ring counter whose truth table is as shown here. We are going to employ a data flip-flop whose characteristics is as indicated. This next state corner map with an input D and present state Qn. The next state is the data. So regardless of the present output 0, 1, the next will be 0, 0, if D is 0. If D is 1, the next state is 1. What we like to do is using this truth table of the 4-bit Johnson counter. First, develop a one-map method for data flip-flops, or sometimes called universal map method. We introduce 4 symbols. Capital I for turning on, @ sign if the flip-flop turn off, 0 if it stay off after clocking, 1 if it remain on or stay on after clocking. The meaning of that is the present 0 becoming 1 as an X if it turn on. And we know the data 1 as an input to make that happen after clocking. For turn off, meaning present state is 1, clocking it becomes 0, so you need a 0 data according to here. Stay off, meaning to say presently 0, after clocking becomes 0, remains 0, data input must be 0. Stay on, present is 1, clocking it, remain 1, that is it. We're going to develop the 4-bit data flip-flop made up of A, B, C, D, and implement that in Xilinx Webpack version 9.1 schematic source. So this is a preliminary tutorial without requiring writing VHDL, but instead just implement it as a schematic in the schematic capture of the Webpack. The next step is to derive the data input reading rule. As we have recalled a while ago, the very symbol for turn on, turn off, stay off, stay on is as shown. In order to derive for the input D of a given circuit, according to here, when you group it in the usual map method, you enclose the 1 and you avoid the 0. So the corresponding one map is you enclose turn on symbol and stay on, while avoiding turn off and stay off symbol. So that is the meaning of this reading rule. To derive the data input, you must include the new grouping to produce the input D, enclosing the I and the 1, while at the same time avoiding enclosing 0 and turn off. And if the don't care X help, you can include it. The third step is to derive for our 4-bit Johnson counter the required data input. Based on the truth table we have presented, It is very easy to fill this 4-variable kernel map for each of the data input of the 4 flip-flop. So here is what happened to flip-flop A. For instance, in this cell, when the table row is 0, 0, 0, when it moves to the next row, the flip-flop A stays off. And over here, the flip-flop, it is not even available in the table, so we put don't care. Over here, we have an I. So the A turn on. And over here, the flip-flop A turn off. Similar reasoning for the others. So applying the rule, remember, we must include I or 1, but not 0 or turn off. So this is the best grouping where the data input is B. And here is for the data of flip-flop B, while avoiding 0 and turn off. So that is C, the input to B data input. For the next flip-flop C, the data input is D, output of D flip-flop. And for the last D flip-flop, the D data input is A complement. So using this, we can now draw the schematic. But before we do that, in Webpack schematic feature, we have to decide what we have to assign to the field programmable array pin number for each of our signals. This is what we're planning to do.